In this module, we will examine how to use the heat balance equation to calculate a person's rate of heat loss or gain, or in other words, their rate of heat storage. There are 5 major modes of heat production and transfer into and out of the human body. There's metabolism, radiation, conduction, convection, and evaporation. Because conduction is a relatively minor component of heat transfer, we're going to ignore it for the purposes of the example that we're going to go through today. So imagine that there's a 5-year-old girl who has just come out of a swimming pool and is sitting outside under a shady tree on a hot summer day. Temperature is 35 degrees Celsius, winds are 5 miles per hour, relatively windy, humidity is 50%, relatively dry. She's wearing a swimsuit covering about 10% of her body. Her total body area is 0.7 meters squared. The temperature of her skin is 30 degrees Celsius. Her skin is completely wet. So we want to calculate her body's rate of heat storage. To do this, we're going to use the heat balance equation. The heat balance equation includes a heat production component, which is metabolism minus work. So any amount of metabolism that is not used to do work results in heat production. It will also include a heat loss component. So the heat loss component is the amount of heat that is transferred from radiation, convection, and evaporation. Generally, these values R, C, and E are going to be positive, meaning that there's going to be a loss of heat from the body through these modes. R and C can also be negative, and if they are negative, that means that there's actually a gain of heat through these modes. E is always going to be positive. It's not possible to gain heat from evaporation. It's only possible to lose it. We can then use heat production and heat losses to solve for the rate of heat storage, or S. If S is negative, that means that there's an overall loss of heat from the body over time. If S is positive, that means there's an overall gain of heat into the body over time. To calculate S for this 5-year-old girl, we're going to use the equations shown here. So for R, C, and E, and then we're going to use this equation to convert miles per hour to meters per second for airspeed. We're also going to use these assumptions. So the girl's rate of metabolism is at basal levels. 20% of her metabolism is used for work. This is her radiant heat transfer coefficient, which is typical for the human body. Objects in the environment that are radiating heat have a temperature that is equal to the ambient temperature. Only skin that is exposed or not covered by her swimsuit will undergo heat transfer. We'll then use the heat balance equation to solve for S. The first thing we want to do is solve for metabolic heat production. Again, we are assuming that metabolism is at basal levels and 20% of her metabolism is used for work. We can calculate the girl's basal metabolic rate using this chart. On the x-axis is age, and on the y-axis is basal metabolic rate, expressed in units of watts per meter squared, where meter squared refers to the surface area of the body. There are 2 different curves, one for females, one for males. The girl's age is 5, so we can go up to the female curve, go over to the y-axis, and we find that the girl's basal metabolic rate is 55 watts per meter squared. So the girl's metabolism is 55 watts per meter squared times the surface area of her body, which is 0.7 meters squared, which gives us a metabolism of 39 watts. The amount of work that the girl is doing is her metabolism times 20%, which is 7.8 watts. The amount of heat production then is her metabolism, 39 watts, minus her work, 7.8 watts, which is equal to 31 watts of heat production. We can then plug that into our heat balance equation. So we now have S equals 31 watts minus R plus C plus E, and we can now solve for R. So R is determined by this equation. R equals H radiant times the temperature of the skin minus the temperature of the radiant environment times the surface area that is available for heat transfer. The radiant heat transfer coefficient, again, is 4.7 watts per meter squared per degree Celsius. We're assuming that the temperature of the radiant objects in the environment is equal to the ambient temperature. And we're again assuming that only exposed skin undergoes heat transfer. We can now plug our values in to solve for R. So we plug in 4.7 watts per meter squared per degree Celsius for the radiant heat transfer coefficient. We plug in 30 degrees Celsius for the temperature of her skin. We plug in 35 degrees Celsius for the temperature of radiant objects in the environment. And then we plug in 0.7 meters squared for her total body area and 90% for that which is exposed and can undergo heat transfer. When we solve for R, this results in negative 15 watts. The fact that it's a negative number means that she is actually gaining heat through radiation, and that's because the environment is warmer than her skin. Next, we want to solve for C, convective heat transfer, which is determined by the convective heat transfer coefficient, the temperature of her skin, the temperature of the ambient environment, and then the area that is available for heat transfer. To determine the convective heat transfer coefficient, we can use this graph. On the x-axis is airspeed in meters per second, and on the y-axis is convective heat transfer coefficient in units of watts per meter squared per degree Celsius. As you can see, as airspeed increases, the convective heat transfer coefficient also increases almost linearly. We know that the airspeed is 5 miles per hour, and so we need to convert that into units of meters per second. We can use this conversion factor to determine that 5 miles per hour is equal to 2.3 meters per second. We can then use this value and this graph to determine the convective heat transfer coefficient for that airspeed, which is about 21 watts per meter squared per degree Celsius. We can then plug that value in along with the temperature of the skin, the temperature of the ambient environment, the girl's body surface area, and the percentage that is exposed, 90%. And then we can solve for C. And when we do that, we get a negative 66 watts for C. The fact that this is negative, again, indicates that the girl is gaining heat through convective heat transfer. And that's again because the ambient environment is warmer than her skin. The final heat transfer component that we will solve for is E, which is equal to the evaporative heat transfer coefficient times the difference between the vapor pressure of her skin and the vapor pressure of the ambient environment times the surface area of her body that is available for evaporative heat transfer. To determine the evaporative heat transfer coefficient, we will use this graph. On the x-axis is airspeed in meters per second, and on the y-axis is the evaporative heat transfer coefficient in watts per meter squared per torr. As you can tell, as airspeed increases, the evaporative heat transfer coefficient increases also. And this is an indication that evaporation happens more quickly when the airspeed increases. To determine the evaporative heat transfer coefficient, we need to start on the x-axis with the value of the airspeed at 2.3 meters per second, go up to the curve, and then over to the y-axis. And we can tell that the evaporative heat transfer coefficient is 50 watts per meter squared per torr. We can now plug in the value of the evaporative heat transfer coefficient into our equation for evaporative heat transfer. We can also plug in the surface area available for heat transfer via evaporation. And what we're left with is an equation that requires values for the vapor pressure of the skin and the vapor pressure for the ambient environment. To determine those values, we can use this graph. On the x-axis is temperature in units of degrees Celsius. On the y-axis, saturation vapor pressure in units of torr. As the temperature increases, the saturation vapor pressure also increases. Saturation vapor pressure refers to the vapor pressure produced from skin that is completely wet or from air that is completely saturated or at 100% humidity. So we know that the temperature of the skin is 30 degrees Celsius. We can use that information to determine that the saturation vapor pressure for skin that is 30 degrees Celsius is 32 torr. To determine P ambient, or the vapor pressure of the ambient environment, we need to multiply the saturation vapor pressure at the temperature of the ambient environment by the relative humidity. The temperature of the ambient environment is 35 degrees Celsius in this case. We can go up from the curve to determine the saturation vapor pressure, which is 42 torr. We then need to multiply that by the relative humidity, which is 50%. And that gives us a value of 21 torr for the ambient vapor pressure. Visually, this is basically half the saturation vapor pressure because the relative humidity is 50% or half. We can now plug the values in for P skin and P ambient into our evaporative heat transfer equation, and we can solve for E, which gives us a value of 350 watts. The fact that this value is positive indicates that the girl is losing heat via this mode of heat transfer. We are now finally ready to solve for S because we know the amount of heat that is produced through metabolism, we know the amount of heat that is transferred from radiation, convection, and evaporation. One thing to note here is that the largest value within any of these components is from evaporation, which means that the amount of heat that is lost from evaporation is going to dominate the heat storage rate. When we solve for S, we obtain a value of negative 238 watts. The fact that this is a negative value indicates that the girl is losing heat from her body. She's losing it at a rate of 238 watts. This means that this girl is going to start feeling chilly under these conditions.